Okay, so those previous problems that we looked at were all able to be solved using a one-to-one technique. These next few problems I'm going to show you that's not the case. So we're going to have to solve these problems in what I call the long way, or we're going to turn them into logs in order to get that variable we're trying to solve for, to get it down to the main line so we can figure out who it is. So first of all, this first equation, we only see one exponential. I need to isolate the exponential first. So let's isolate the exponential, then we can decide if we think it's one-to-one or not. We're going to do that by subtracting 7 from both sides. I can then rewrite that as negative 2e to the x equals negative 2. And then if I divide both sides by negative 2 to get this exponential by itself, I'm actually going to end up with e to the x equals 1. So this is actually the exponential problem I'm going to solve. The e and the 1, those are not the same. It's not the same base. I can't make it the same base. So I'm going to do this the long way, which I can do one of two ways. I can either backwards map it into a log, or I can take the log of both sides. Let's go ahead and do the log of both sides on this one. So what I'm going to do, I'm going to write the word log in front of both sides. You can do whatever log you want, as long as they match. And so I'm going to do the natural log of both sides in this case. And you'll find that when your base is an e, the natural log is really the best one to use. It helps the problem simplify here in just a second. I'll show you what I mean. So now that we have this written as the log of something to a power, we can use that log rule to drop that exponent down in front. So this actually now is x times the natural log of e equals the natural log of 1. And from our log rules, we actually know that the natural log of e, that's actually just 1. And so if that's a 1, I really have x times 1 equals the natural log of 1. So if I simplify that, it's actually x equals the natural log of 1. Now, if you really, really know your log rules, you'll actually know that the natural log of 1 is, in fact, 0. So the answer to this problem in its most simple form is actually x equals 0. Okay, let's look at the second problem. The one that makes this one interesting is because you have a single exponential term, but it's actually in the denominator. So number one, we need to get that x out of the exponential position, but more importantly, first we need to get this exponential expression out of a denominator. One way to do that is to cross multiply. When you have a fraction equals a fraction, we can cross multiply. Another way is if you have a fraction equals a fraction, you can actually take them both and invert them. Let's just do the cross multiplication. So 100 times 1, that equals 100. And this term times 1 will just equal that term. So I have 1 plus e to the 2x. So now this looks more like the problem that we had above, where we see a single exponential, it's on the main line, and now our goal is to get this x down to the main line. I'm going to subtract 1 so that I can isolate that exponential. Subtracting 1 from both sides gives me 99 equals e to the 2x. Okay, so now this is definitely an exponential. The exponential is isolated, and e and 99 are not the same. I can't make them the same. So I'm going to do this the long way. I'm going to turn it into a log. Now the problem above, I took the log of both sides. This one, how about we practice just backwards mapping it? So if you remember to backwards map, we're going to turn it into a log. This number that's by itself over here goes inside the log. The base of the exponential becomes the base of the log. And this, the exponent, gets broken out by itself. So now we have taken this exponent and we have brought it down to the main line, which is what we need to do to solve this. Isolate the x, simply divide both sides by 2. So this, if I cross that off, this is what x equals. But there's a little simplifying I can do there. X actually equals, when I have log base e, remember there's a better way to write that. That's called the natural log. So natural log of 99 divided by 2. And this will be my answer for x. Now if I had chosen, once I got to this point, to take the log of both sides, I would have gotten the exact same result. Okay, let's look at another one quickly. So this problem, we actually have two exponentials. You see that that variable we're trying to solve for is actually in both places. So this one's interesting. This is a 2, this is a 3. I can't make that 1 to 1. I'm not going to be able to turn one into the other, so I'm going to have to do this the long way. But when you have two exponentials and you have that unknown in both places, you actually can't backwards map these. We're going to just take the log of both sides. And again, it doesn't matter which log we want to do. So I'm just going to do, let's say, log base 10. So there we go. I've written the word log in front of both. Now that they're written as logs, we can use that skill of bringing those exponents down to the main line. So I'm going to rewrite this as x plus 1 times the log of 2 equals x times the log of 3. So this problem is interesting again because we have the x on both sides of our equation. So if you remember, algebra skills say that when you have your x in more than one position, if it's linear, we want to get all the terms that have the x on one side of the equation and the terms that don't have the x over onto the other side. So I'm going to actually distribute this log of 2 in and rewrite this as x times the log of 2 plus 1 times the log of 2, and you don't really need the 1 there, I just did it for emphasis so you could see the distribution, and that equals x times the log of 3. So when I look at this equation now, this term has an x in it and so does this one. So I want to get those terms onto the same side of the equation. This does not have an x, so I'm going to shoot it over to the other side, and actually so I can keep that positive, I'm going to bump this one over. So this can be simplified as log 2 equals x times the log of 3, and then if I subtract that over, I get minus x times the log of 2. Now, the reason that was a powerful tool is because now that I have only expressions that have x in it on this side, I can actually factor that x out as a GCF, and that will allow me to isolate it into a single location. So I have log 2 equals, if I factor that x out front, I actually have log of 3 minus log of 2. And if you're not sure if you did that right, you can always push this back in to confirm that you get what you had above. But now, now that x is finally in one spot, in order to isolate it, this just needs to go away. And since it's multiplied, I'm going to divide. So if I literally just divide both sides by this expression, I will be able to have x finally by itself. So these basically go away. So now I have x equals log of 2 divided by log of 3 minus log of 2. And that would be my final answer. If I wanted to, if my instructor wanted me to write it as a decimal, I would then plug that into a calculator and get it expressed as a decimal. Okay, one last quick example. This is a really interesting example. They don't show up very often, but this is one you have to be careful. You see an exponential show up in 2 positions, but actually if you look at those very carefully, they don't match. They're not the same. And this actually looks more like a trinomial, if you remember those trinomial days and factoring trinomials. And if you take a close peek, this is actually quadratic-like, and we could actually go through a full substitution technique to solve for this. What I want to call out is that if you know how to solve this quadratic that's factorable, you actually know how to solve this one that's quadratic-like. So if we take this middle term, if we square that, that's what we have here. So we're going to be able to factor this like a trinomial, where this is actually the piece that we're going to map here and here. So these are basically the same trinomial, it's just one of them has an x and one has an e to the x. So really quickly I'm going to just factor this like this. We actually have an e to the x in both positions, and then we still have the minus 3 and the plus 2. I know I did that quickly, but what I wanted to call out is we now have 2 exponentials that we need to solve according to zero product property. This one will look like this, and the second one will look like this. So if we isolate those exponentials, we can do this one by subtracting 2 over, we can do this one by adding 3. We actually end up with e to the x equals 3. And over here we end up with e to the x equals 2. I wanted to call out this example because what we can learn from this is we can backwards map these, we can take the log of both sides. Whichever method you choose to use, you'll show that this one actually has an answer. You actually get x equals the natural log of 3 if we were to do that one. This one, however, because this is negative, there's actually no solution to this part of it. If you're not sure about that, you could backwards map it or log both sides and drop that x down. Either way, you end up with an expression where you're trying to take the log of a negative number, which you are not allowed to do. And that's why this piece, there isn't an answer, only this piece. So we do have one answer, x equals a natural log of 3. Again, so in this material, the important thing I want to stress is we are solving exponentials, which means that variable is up in the exponential position. We need to get it to the main line. We do that in one of two ways, utilizing one-to-one property or utilizing inverse property. One-to-one is the fastest, slickest way to go if it applies. If it doesn't apply, we're going to need to do it the long way. I hope these examples were helpful, and I'll see you in the next video.